Hello, my name is Jesse Baker and I'm an applications engineer supporting position sensing products. In this video, I will discuss magnet temperature compensation. The residual magnetism or remanence of a permanent magnet is an indication of the magnetic flux density of the magnet and is denoted by the letters Br. The remanence of a permanent magnet will change based on the temperature. This change is often defined as a negative temperature coefficient or as a positive reversible temperature coefficient in terms of either Br percent per degrees Fahrenheit or Br percent per degrees Celsius. This chart shows an example of the negative temperature coefficient denoted as alpha for a range of different magnet types. This plot also shows the change in remanence for some magnet types over the temperature range of negative 50 degrees Celsius to positive 150 degrees Celsius. Note that, in general, the remanence of a magnet decreases as temperature increases. Since remanence for a permanent magnet changes over temperature, the magnetic field of that magnet will also change. This plot shows the magnetic field strength for the example magnet described on the left at a few different temperatures. Note that the impact due to temperature is larger closer to the magnet because the change in remanence is a percentage, not an offset. When configuring magnet specifications in TIMS, there is a field for specifying the temperature coefficient for the magnet. This will have a default value depending on the magnet material that has been chosen. Additionally, a custom value can be entered if desired. TI offers magnetic position sensors that are designed to adjust sensitivity automatically to compensate for the remanence change in magnets across temperature. In some cases, the sensitivity temperature coefficient is fixed for a specific device orderable, as shown in this excerpt from the DRV 5055 datasheet. The A variants of the DRV 5055 have a sensitivity temperature compensation of 0.12% per degree Celsius, while the Z variants have a 0 sensitivity temperature compensation. In other cases, the temperature compensation may be user programmable, as shown in this excerpt from the TMAG 5170 datasheet, which offers a temperature compensation register to allow the use of no temperature compensation or neodymium, samarium cobalt, and ceramic magnet types with coefficients of 0, 0.12, 0.03, and 0.2% per degree Celsius respectively. If a device has temperature compensation enabled, the temperature compensation field will be shown in TIMS under the Sensor Specifications tab. Depending on the type of sensor, this field may have a drop-down option, or it may be fixed according to the part number selected. On the left, an example of a device with programmable temperature compensation is shown, whereas on the right, an example of a device with a fixed temperature compensation is shown. In a system, if the magnetic position sensors are not compensated as needed, then the output voltage will decrease as temperature increases due to the decrease in remanence of the magnet. Without sensitivity compensation, the magnet would then need to be moved closer to the sensor to get the same output voltage. In these simulation results, I have run a slide-by simulation with a neodymium magnet at two different temperatures. We see the Z component of the magnetic field in the first plot and the corresponding device output in the second plot at temperatures of 20 degrees Celsius in blue and 125 degrees Celsius in green, with no temperature compensation enabled. Note that the magnetic field density curve is different for each plot at the different temperatures due to the temperature coefficient of the magnet. In these results, we see the same simulation, but now with a sensor temperature compensation of 0.12 enabled. Note that on the first plot, the magnetic field densities are different at the two different temperatures, but now the device output plot curves are very closely matched despite the different temperatures. This is because the sensor temperature compensation of 0.12% per degree Celsius is working to account for the magnet's temperature coefficient of negative 0.12% per degree Celsius. That explains magnet temperature compensation. To learn more about TIMS and the impact of temperature on magnetic position sensing applications, please see the relevant collateral linked here. To get started on your magnetic simulation with or without temperature compensation, please visit www.ti.com/TIMS.